right now, I mean, literally as we speak, people all over the world are dropping thousands of dollars on these viral salmon sperm facials.
Yeah, it's everywhere.
Right. And they're hoping to walk out of the clinic with that perfectly regenerated glass-like skin. But according to the latest clinical guidelines in our stack of sources today, there is a very high chance that half of these clinics are injecting the completely wrong molecule for the job.
Which is, honestly, a fascinating oversight, especially when you consider just how advanced aesthetic medicine has become lately.
Yeah, you'd think they'd have this nailed down.
You really would.
Hmm.
But the literature we are looking at today, which spans recent dermatology journals, bioengineering patents, and aesthetic medicine reports, it points to a massive misunderstanding in the industry.
Mm.
It turns out the magic isn't just in the raw material itself.
It's the size, right?
Exactly. It all comes down to the microscopic architecture of the molecule they're actually using.
Well, welcome to today's deep dive. We are taking a microscope to arguably the hottest trend in regenerative aesthetics. Our mission today is to cut through all that slick marketing buzz.
And there is a lot of buzz.
So much buzz. We want to explore the precise microscopic differences between two closely related biopolymers. So that's PDRN, which stands for polydeoxyribonucleotide, and PN, which is highly concentrated polynucleotides.
Right. We're going to decode exactly how the polymer chain length and the molecular weight of these DNA fragments completely dictate how they behave inside your skin.
Because the aesthetic industry has basically treated those two terms as completely interchangeable for years, haven't they?
Oh, absolutely. And that lack of distinction has led to wild inconsistencies in clinical applications, which is exactly what the new 2025 and 2026 scientific literature is finally trying to correct.
So whether you're a skincare enthusiast sitting there wondering what exactly is in those viral injectables you see on social media, or maybe you're just a curious learner who geeks out over molecular biology, this deep dive is going to give you that ultimate aha moment.
Yeah, about how manipulating DNA chain lengths literally changes cellular behavior.
But I guess we have to start at the very beginning, right? The foundation of both PDRN and PN, the raw material.
Right, because both of these biopolymers originate from the exact same place. They are DNA extracted from the sperm cells of trout or salmon.
Which is known industrially as milt, right?
Yes, exactly, milt. And our patents actually specify the exact species. It's Oncorhynchus mykiss, the rainbow trout, or Oncorhynchus kDa, which is the chum salmon.
The marketing teams clearly love leaning into the exotic, slightly shocking nature of that. Like salmon sperm facial just gets clicks.
Oh, definitely. It's provocative.
But we should clarify why scientists actually chose this specific source. I mean, it isn't because aquatic creatures have some mystical healing property.
No, not at all. The reasoning is purely pragmatic and biological. Salmon sperm is just an incredibly abundant, reliable source of nucleotides.
Because they can harvest and purify it at an industrial scale.
Exactly. And crucially, the DNA from these specific salmonid fish is up to 95% genetically similar to human DNA.
Wow, 95%.
Yeah, it's very high. And that high degree of genetic homology makes it remarkably biocompatible. So your immune system is highly unlikely to view it as a threat.
But they don't just extract the milt and, put it straight into a sterile syringe.
I hope not.
Right. The purification process detailed in these bioengineering patents is intense. They subject this raw material to extreme high heat purification.
Hitting temperatures up to 135 degrees Celsius.
Which, when I read that, it seemed completely counterintuitive. Normally, if you expose a biological compound to boiling heat, you destroy the active ingredients.
Well, that would be true if the active ingredient were a protein. Proteins have very delicate three-dimensional structures.
What they call their tertiary structure, right?
Exactly. And those structures are held together by relatively weak bonds. So when you heat them, those bonds break, and the protein irreversibly unfolds.
Like cooking.
Yes. Think of frying an egg. The clear albumin turns white and solid. You can't unfry it. But DNA is fundamentally different.
Because the genetic information in DNA is protected by a tough, covalent sugar phosphate backbone.
Right, and that covalent backbone is incredibly resilient. The extreme heat of 135 degrees basically causes the double helix to temporarily unzip.
Oh, so the hydrogen bonds between the base pairs just separate.
Exactly. But the actual chain of nucleotides remains totally intact. Meanwhile, all the cellular proteins, the lipids, and the peptides in that raw material are completely destroyed. They just melt away.
And then it cools down.
Yeah, once the mixture cools, the DNA strands just zip right back together.
I see. So I was thinking about it like this. It's like stripping a house down to its foundational lumber.
Oh, I like that.
Yeah, by removing the drywall, the paint, the fixtures, which are the proteins and lipids, you remove the things that cause allergic reactions or immune rejection.
Right, because you're stripping the hazard away, leaving behind only the pure biocompatible structural beams.
The DNA itself.
Exactly. You're left with a nucleotide mixture that the literature states is over 95% pure. It's the pure genetic structural code, completely devoid of the cellular machinery that would cause a human body to flag it as foreign fish tissue.
That brings us to the historical chaos in the clinics, though. So we have this perfectly pure, biocompatible salmon DNA. But for years, clinicians were buying products labeled PDRN or PN and getting wildly different results.
It was a huge problem.
Right, like a doctor might inject what they thought was a fluid, fast-acting serum to heal a laser burn, only to find they had injected a thick structural gel.
Which would cause lumps under the patient's skin.
Exactly, because the lack of standardized nomenclature just created a mess.
Manufacturers were producing molecules of vastly different sizes and just slapping whatever trendy acronym they wanted on the box.
But then the 2025 and 2026 scientific literature finally stepped in to clean up this Wild West, and they introduced a standardization called the Marquis polynucleotide cutoff.
This is such a critical pivot in the field.
Yeah, and this is the core concept for you to keep in mind as we go forward today. The difference between PDRN and PN is not the source material. The difference is strictly their molecular weight and their polymer chain length.
Right. The Marquis cutoff establishes a hard dividing line at exactly 1,500 kilodaltons, or kD.
And kilodaltons are just the unit of measurement we use for molecular mass, right?
Correct. So anything below 1,500 kilodalton is legally and scientifically classified as PDRN.
And anything at or above 1,500 kilodalt is classified as PM.
Exactly.
Okay, but I'm going to challenge the mechanics of this for a second. Because if PDRN and PN come from the exact same raw salmon DNA, how do they get those different weights? Like if you take chemical scissors and start hacking this long salmon DNA into tiny fragments to make PDRN, aren't you destroying the genetic code?
Well, yes, you are breaking it up.
So why doesn't the human immune system just recognize those floating fragments as viral debris or like cellular garbage and dispatch white blood cells to flesh it out?
That is a fundamental question about how our immune system actually recognizes threats. Our macrophages and immune cells are primarily scanning for foreign proteins.
Okay, so specific amino acid sequences.
Right, sequences that look like bacterial walls or viral capsids. They are not looking for raw nucleotide sequences because nucleotides are the universal building blocks of all life on Earth.
Oh, wow. So an adenine base in a salmon is indistinguishable from an adenine base in a human.
Exactly. As long as the purification process has stripped away those fish proteins we talked about, your body just sees these DNA fragments as loose, raw materials.
Okay, so the immune system ignores it. But how do the manufacturers actually control the cutting process to hit that 1,500 kDa cutoff? They obviously aren't using microscopic scissors.
No, they use a process called enzymatic hydrolysis.
Enzymatic hydrolysis.
Yeah. Scientists introduce specific enzymes called endonucleases into the pure DNA mixture. These enzymes bind to the DNA and cleave the phosphodiester bonds at specific sites.
So they basically act like chemical scissors.
Pretty much. And the manufacturers control the exact molecular weight by strictly regulating the temperature, the pH, and the time the enzymes are allowed to work.
It sounds kind of like editing a film roll. If they want to create PN, they use a very gentle, brief enzymatic process that preserves the long, intact ropes of DNA.
Right, they keep the chains long.
But if they want to create PDRN, they let those enzymes run wild, chopping those long ropes into much shorter, highly specific fragments, and then they halt the reaction the moment it hits the desired weight.
You've got it. The precision of that enzymatic control is what allows us to dictate the biological behavior of the molecule once it actually enters the human dermis.
Well, let's explore that behavior then. Starting with the molecules below the cutoff, PDRN, the short-chain fragments. The literature defines this range as 50 to 1,500 kilodaltons.
Which translates to roughly 50 to 2,000 base pairs of DNA.
But the data shows the bulk of PDRN actually peaks much lower, right? Usually between 132 kDa and 350 kDa.
Yes, it's quite small. And because these chains are so short, their physical rheology, which is how the substance flows, is very distinct.
So it's not super thick.
No. PDRN has very low viscoelasticity. It is a highly fluid, watery substance.
But the real magic isn't just that it flows easily. The size dictates its cellular function. I was reading about the adenosine A2A receptor, and it completely blew my mind how specific this interaction is.
It is incredibly specific.
PDRN's short chain length basically allows it to physically bind to this A2A receptor on the surface of our cells.
Right, and molecules that fall outside of the specific molecular weight range simply do not have the spatial configuration to bind with that receptor effectively.
They just don't fit.
Exactly. But when PDRN docks with the A2A receptor, it initiates a profound biochemical cascade inside the cell. It downregulates pro-inflammatory cytokines like TNF-alpha, heavily suppressing inflammation.
And beyond just stopping inflammation, it actually shifts the cellular environment into a regenerative state, doesn't it?
It does. It promotes the secretion of VEGF.
Vascular endothelial growth factor.
Right, which literally signals your body to grow new, microscopic blood vessels to feed damaged tissue.
Wow.
And I would add that triggering the A2A receptor has a fascinating effect on fibroblasts. We know fibroblasts are the cells responsible for producing collagen and elastin.
Right, the stuff that keeps skin looking young.
Yeah, exactly. But as we age or endure UV damage, fibroblasts often enter a state of cellular senescence. They basically fall asleep and stop working.
And PDRN wakes them up.
It prevents that senescence entirely. It forces the fibroblasts to remain active and proliferative.
That's amazing as a signaling molecule. But PDRN has a completely different mechanism of action too, right? The one that relies on the nucleotide salvage pathway.
Yes, this pathway is crucial to understanding why PDRN is so regenerative. To synthesize new DNA for cell division and tissue repair, your cells typically use the de novo synthesis pathway.
And the de novo pathway is exhausting. Let's use an analogy here. Imagine your skin cells are construction workers trying to repair a damaged building.
Okay, I can picture that.
If they have to use the de novo pathway, it means they have to manufacture every single brick from scratch. They have to mine the raw clay, process it, bake it in a kiln, and transport it.
Biochemically, that requires a massive expenditure of ATP, which is cellular energy. It is incredibly taxing on the cell's metabolic reserves.
Especially when the tissue is already compromised or aging, right?
Exactly.
But injecting PDRN is like backing a dump truck up to the construction site and dropping off a massive pile of pre-cut, perfectly salvaged bricks.
That is a perfect way to describe it.
Instead of your body expending all that metabolic energy manufacturing new building materials to fix damaged DNA, the cellular workers can simply utilize the salvage pathway to recycle those PDRN fragments.
And the energy savings there cannot be overstated. Because the cells are bypassing the energetic cost of de novo synthesis, they can redirect all of that conserved ATP toward producing fresh collagen.
Upregulating elastin production too, right?
Yep, and actively repairing the surrounding extracellular matrix. PDRN is fundamentally an energy-saving biological shortcut.
Which completely explains why it's considered the fast-acting repair crew. Now let's cross the Marquise cutoff line and look at the heavyweights, PN, or highly concentrated polynucleotides.
We are crossing into a completely different physical and structural realm now.
By definition, PN sits at a molecular weight of 1,500 kDa or higher, and some of the newer formulations detailed in the patents boast PN chains reaching 8,000 or even 10,000 kDa.
Which is massive on a molecular scale.
Yeah.
And that massive chain length completely alters the physical nature of the resulting gel.
Because the chains are so incredibly long,
They tangle up with one another.
Right. I picture it like a massive, dense bowl of tangled microscopic spaghetti.
That's exactly what it looks like structurally. It becomes highly viscoelastic.
Yep.
It is thick, it is porous, and when it is injected, it doesn't just flow away like PDRN.
It forms a persistent three-dimensional matrix directly in the dermis.
Yes. And the physical presence of that matrix introduces a hydration factor that is exponentially stronger than PDRN. Long DNA polymers have a staggering capacity to attract and hold water molecules through hydrogen bonding.
Yeah, the clinical guidelines noted that just for the monolayer content, which is just the first innermost layer of water binding to the molecule, a DNA strand can bind 2 water molecules per individual nucleotide.
Right.
When you scale that up to a polymer chain that is 10,000 kilodaltons long, the hydration power is astronomical.
Those tangled chains act like a deep tissue sponge, drawing moisture into the dermis and expanding the physical space between cells.
But put yourself in the patient's shoes for a second. If you inject this massive, thick, viscous sponge under the skin, wouldn't it just sit there like a palpable lump? I mean, that sounds like a complication waiting to happen.
Well, you'd think so, but that slow degradation is the exact intended purpose of PN.
Really?
Yeah, it is not meant to be a rapid repair signal that flushes through the system. Its primary role is structural.
Mm.
As it sits there and very slowly degrades over a period of weeks or months, it acts as a biostimulatory scaffold.
Oh, so it's providing immediate physical volume in areas that are hollowed out, like uh, deep under eye circles.
Yes, the volume is the immediate effect. But the long-term biological effect is that the patient's own fibroblasts actually migrate into that tangled 3D spaghetti matrix.
They move into it.
They do. They attach themselves to the PN scaffold and use it as a stable framework to lay down dense, organized bundles of fresh collagen over a sustained period.
Which perfectly highlights the clinical synergy of these two molecules. For you listening, understanding the cellular biology is fascinating, but seeing how this dictates real-world treatments is where it all clicks together.
Because the literature makes it abundantly clear that PDRN and PN are not rival ingredients fighting for supremacy in the skincare world.
They represent two specialized points on the exact same biomolecular spectrum.
Exactly.
PDRN is the intensive repair signal. Because it's short and fluid, it spreads quickly. Clinicians use it for rapid skin soothing, accelerated wound healing after intense laser treatments, treating atrophic acne scars.
And delivering that powerful A2A receptor-driven anti-inflammatory action to deeply compromised skin.
Right. And PN, conversely, is the sustained rebuilding framework. Clinicians use it when the goal is deep structural remodeling.
It is utilized for lifting sagging tissue, providing intense, long-lasting dermal hydration, and physically correcting deep wrinkles and overall skin laxity through sustained biostimulation.
So to put it simply, you wouldn't use massive structural scaffolding to try and plug a sudden acute plumbing leak?
No, you wouldn't.
That's PDRN's job. Get in there, fix the immediate damage, shut down the inflammation, and apply the salvaged bricks. And you wouldn't use a tiny little wrench to try and hold up a collapsing ceiling.
That's what PN is for, providing that heavy-duty, long-term structural support matrix.
So when clinicians finally grasped the mark cutoff, it revolutionized their practice. They stopped treating these DNA fragments as a generic salmon DNA catch-all.
They began using them as precision medical tools, tailoring the exact polymer chain length to the specific anatomical needs of the patient.
Which means the next time you hear about a DNA-based regenerative treatment or you see an influencer raving about a salmon sperm facial, you are going to know the actual science behind the buzz. The regenerative power isn't just that the raw material came from a fish.
No, the true biological trigger relies entirely on the precise length of the polymer chain. Manipulating that length determines whether you are sending a fleeting, powerful repair signal or laying down a lasting structural foundation.
Before we wrap up this deep dive, though, there is one final, really provocative concept from our stack of sources that you need to think about. We spent this entire time talking about injectables.
Right. Physically bypassing the body's natural armor with a needle to deliver these polymers into the dermis.
But the beauty market is currently flooded with topical salmon DNA products. Serums, creams, sheet masks.
The proliferation of topical PDRN in consumer skincare is massive right now. But it directly collides with one of the most fundamental laws of dermatology.
The 500 Dalton rule.
Yes.
This is a bedrock concept of skin permeability. It dictates that, broadly speaking, only molecules with a molecular weight under 500 Daltons can passively cross an intact human stratum corneum.
Which is the tough outermost barrier of your skin.
Yeah.
And 500 Daltons is incredibly small.
Keep that number in your head, 500. Because if we look back at the molecular weights we decoded today, even the absolute smallest, most aggressively fragmented PDRN chains peak at around 50,000 Daltons.
Right.
And those massive PN structural chains, they are sitting at 1,500,000 Daltons and beyond.
So from a purely biophysical standpoint, they are orders of magnitude too large to squeeze through the lipid matrix of the skin barrier on their own.
Think about the implications of that. With all of these trendy, heavily marketed salmon DNA creams and serums hitting the shelves, how many of those highly purified, expensive DNA fragments are actually penetrating your skin to reach those adenosine A2A receptors in the dermis?
And how many of those massive polymer chains are just sitting completely trapped on the dead surface of your skin, entirely unable to trigger that biological repair cascade?
It's definitely something for you to mull over the next time you find yourself browsing the skincare aisle, holding a very expensive jar of cream.